5.6 Characteristic reactions of acids. Now we have studied acids, alkalis, bases, antacids, their differences. Now comes the part where we discuss their characteristic reactions. We actually start with acids. It's better or easier to start with acids and then move on to salts. All acids take part in neutralization reaction. Now, are there any other characteristic reaction? The answer is yes. Now we got to go with these acid reactions, but in order to bifurcate them, what we do is something like this. A reactive metal can react with an acid, for example, magnesium or zinc. The reactions are like this. We already know about the bubbling and the effervescence part. The quicker the reaction, the more hydrogen they are going to give off, which causes this whole bubbling or effervescence. It's also going to produce a salt. We already know that. Moreover, the second one is a base or an alkali, which is actually a neutralization reaction. And the last one is a metal carbonate or a metal hydrogen carbonate. These three characteristic reactions of acids actually give us the salt. In a neutralization reaction, the hydrogen ion of the acid is replaced by a metal to give the salt. That's how we define the salts. Actually, the salts are both made up of acids and a component of base, so that's why it has to contain both. So redefining salts, a compound made from an acid when a metal takes place of hydrogen in the acid is known as a salt. That's the easiest definition, and with neutralization reaction, you would be able to understand this definition easily. So moving on, all three reactions are defined on this page. Let's start with the first one. The reactions of acids with metals. It's pretty easy with this scheme that a metal, whenever will react with an acid, would produce Salt plus hydrogen. The hydrogen is given on in the form of bubbling or effervescence. So it's pretty easy to understand how they would react, what the visual observations are. But sometimes the reaction does not occur for elements which are least reactive, such as copper, silver, gold, or platinum. They don't even react or take too long to react. Now, the salt which is made depends upon the acid. These lines are very important. I ask my students to memorize every pink portion on this page, including this one. Hydrochloric acid always gives a chloride salt. Nitric acid always gives a nitrate salt. Sulfuric acid would always give a sulfate salt. Ethanoic acid would always give an ethanoid salt. In the similar way, phosphoric acid would always give phosphate salt. I'm not gonna write the whole line, just the name of the acid and the salt. In the similar way, carbonic acid would give us carbonate salt. So name the acid in the similar way, you would know which salt it's going to give. For example, methanoic acid, methanite salt, the list goes on. So these are pretty much the acids or the salts that we study in our IGCSE syllabus. So it gives us a very good idea what kind of salt we're going to form depending upon what kind of acid we started off with the reaction. Now, if you take examples, magnesium plus nitric acid gives us magnesium nitrate plus hydrogen. So nitric acid gave us nitrate. Now, it's pretty similar when an acid metal reacts with an acid. Take out this hydrogen, replace it with the metal, you'll get the salt. Write the hydrogen as a separate gas. You'll do it in every single reaction. Take out this hydrogen of the acid, replace it with the metal, you'll get the salt, and write the hydrogen as a gas separately. This happens in every single reaction. In most of the reactions, you would notice that the metal was a solid to begin with. The acid was an aqueous solution. The resultant salt was also soluble, hence an aqueous solution, and hydrogen was a gas. So pretty much in all these reactions, the state symbols would remain the same. This is the first one, the reaction of acid with a metal, and it's the easiest one. The second one on the list is reaction of acids with bases and alkalis. Whether it's a base or it's an alkali, the reaction would be known as a neutralization reaction. So acid plus base, or you may also write alkali over here, will give you salt and water. Now the salt produced in this reaction will again depend upon the acid, and this time the base or alkali as well. In order to clear up that idea, they have this diagram on the center of the page where they're discussing sodium chloride as an example. LaCl is the example. In this example of NaCl, the metal comes from the base or the alkali. The non-metallic part comes from the acid. So the chloride part comes from hydrochloric acid, but the sodium comes from the metal or the base or the alkali. So that's how we can bifurcate it. Every time when a salt forms, we can easily bifurcate the salt. Negative part comes from the acid, in this case nitric acid, because it's the nitrate part. This comes from, however, this is a reaction with the metal. This comes from the base or alkali. Let's take examples of those ones, exact reactions. Take a look over here. NaOH reacts with HCl. So NaCl, if we divide it up, Na is actually coming from NaOH and Cl is coming from HCl. And there's water. So it's pretty easy. Acid plus alkali gives us salt plus water, or acid plus base gives us salt plus water. Make sense?
Yes, sir.
All right, good. The third and the last kind is the reactions of acids with carbonates. Acids plus metal carbonates. Remember, in the start of the topic in the previous page, it was also given with metal hydrogen carbonate. So whether it's metal carbonate or it's metal hydrogen carbonate, both react in the same way. Let's joggle your memory. Carbonate was the ion with CO3 -2 charge, and hydrogen carbonate was the ion with HCO3 and just a negative charge. So either this ion is present or this one. In both the cases, the results are salt, water, and carbon dioxide. So you would see in all of these three reactions, salt must form. Either it gives us hydrogen with metal, water with the base or alkali, or water and carbon dioxide both with a carbonate or a hydrogen carbonate. These are the products that accompany salt in this kind of reaction. Again, as hydrogen was produced, there was some bubbling. We can call it bubbling, we may call it fizzing, we may call it effervescence. All three words are acceptable. So the same thing would happen in case of carbon dioxide. As it's a gas, the gas is going to leave the system in the form of bubbles or fizzing or effervescence. So you would see an example reaction for this one on the next page. There you go. So HCl, when reacts with calcium carbonate, gives us a salt, water, and carbon dioxide. Again, divide the salt. Calcium comes from the metal carbonate part. Chloride part comes from the acid. So it happens every time, no matter what the reaction is. The negative part of the salt always comes from the acid. The positive part of the salt comes from the type of reaction. It may come from a metal, it may come from a base or an alkali, or it may come from a metal carbonate. So whatever the case may be, it would always come from these parts. So we have water and carbon dioxide. Usually in books, the reactions or the examples for metal hydrogen carbonate is missing. So I'm going to write one over here. Let's take sulfuric acid, a different acid over here. And let's say we have sodium hydrogen carbonate. This is commonly also known as baking soda. And without this specific salt, we can't bake anything. So this is required for the baking purposes. And this is a pretty good one. Our pizzas, doughs, breads, everything that we bake comes out of this salt. So sulfuric acid, when reacting with this salt, produces Sodium sulfate also produces water and carbon dioxide. This is a balanced equation. So this would also give you the idea that a sulfur salt is formed because of sulfuric acid. The sodium part is actually coming from the hydrogen carbonate in this case. As this is an acid plus metal carbonate or hydrogen carbonate reaction, it's giving us three products: the salt, the water, the carbon dioxide. So there we have all three reactions. I would like to stop at this point and I would like to draw a mind map. So mind maps are easy. Remember, we always start off with acids, and there are actually three kinds of reactions. When an acid reacts with a metal, it gives us salt plus hydrogen. When it reacts with a base or an alkali, it gives us salt plus water. Mind map is going to summarize everything in one place. And when it reacts with metal carbonate or hydrogen carbonate, it is going to give us salt plus water plus carbon dioxide. So I guess this is pretty easy to memorize. And the examples are too. And if you know the basics of how a salt is formed, the negative part comes from the parent acid, the positive part comes from either the metal, base, alkali, carbonate, or hydrogen carbonate, you would always be able to form the correct salt. Remember, these equations are a very common part of past papers. I've never seen a paper without one of these reactions. And asking the student to either complete the equation or to balance the equation or to predict the products or to write the whole equation balanced including state symbols is a common way of asking these questions in Cambridge. Any questions from this specific part? All right. So let's get back to the book then. So on the top of this page, you'll find a big table. Now this table is going to clarify many things for us. If you look at this table, you would see that it starts off with a base, and then there are some salts made, and there are different acids by which we are making those salts. So if it's a hydrochloric acid, something you'd notice is that all the salts are chloride salts. If it's nitric acid, all the salts are nitrate salts. If it's sulfuric acid, all the salts are sulfate salts. It only depends upon the base or the alkali. In this case, the top two are bases, the bottom two are the top two are alkalis, my bad, the bottom two are bases. So you would easily notice that the product changes every time. We started off with sodium, we ended up with sodium chloride in this case. If we started off with potassium, we ended up with potassium nitrate in this case. Or if we started off with magnesium oxide, we ended up with magnesium sulfate in this case. Every time, the name and the formula are written. But in order to get this as a question in Cambridge, completing the equations, balancing the equations, predicting the products, coming up with the right names or right formulae, you must have a good grasp of what we studied back in chapter 3. Remember, there was topic in 3.5 where we studied how to come up with formulae. So you should know if there is a 2 at the bottom of this magnesium nitrate formula, that's because magnesium has a +2 charge, which needs to be multiplied all the way over to the bottom of nitrate. A nitrate has a -1 charge, because of which we don't write anything below magnesium. So we end up with this kind of magnesium nitrate formula with brackets and a 2 at the bottom, subscript. Not just that, for a better understanding or a complete grasp, you should also be able to write their word equations. For that, you need to understand nomenclature in the same topic 3.5. Now, this part of the book goes with many common names, which if you're going to write in exams, you're going to end up getting your marks cut. They're using many common names, that's fine. But remember, in papers, when they ask you for a name, they want you to go with the IUPAC or the standardized name. Remember, in a standardized name, any simple element has the same name, but when it comes to transition metal, the name changes. So this last line, these names are good for this part of the book, but they are not good for your exams. If you're going to write this, it would be copper 2 oxide, copper 2 chloride, copper 2 nitrate, like that, and copper 2 sulfate. Remember, you can't just write copper nitrate or copper chloride or copper sulfate or oxide. That's not the correct way of writing the name in exams. I understand this is written over here, but the books sometimes go with the common names because they are going in the flow. However, it's not about the flow or fluency of the entire chapter in exams. They are testing you with a specific point, and when it comes to a specific point, you need to be able to write the correct names as per the nomenclature rules. So according to the nomenclature rules, if you remember, transition metals have their names and then their valencies, or you can say oxidation states, next to them in parentheses and in Roman numerals. So it would be written something like this: copper 2 chloride, or copper 2 oxide, or copper 2 nitrate, or copper 2 sulfate. So I tend to ask my students, when you're going through this table from the book, make sure you add these two to all 4 of these names. So just because you're looking at it or you're preparing from it, you don't get in the habit of writing the common name casually or habitually. That way, you're getting your marks cut. So it's better to write these 2s over here. So whenever you're preparing for exams, you are also considerate, you put a thought into it, and you come up with the proper name as per the nomenclature rules. So remember the rules that we have studied back in 3.5 for formulae as well as for nomenclature to come up with correct answers. I sometimes ask my students that you can even make a table of your own. For example, if you aren't going to go with these bases, pick up the bases or alkalis from the previous table and write the new ones over here. Change these acids with different acids from the table at the start of this chapter. Instead of hydrochloric acid or nitric acid or sulfuric acid, you can go with carbonic acid or phosphoric acid or ethanoic acid. Then you can come up with the products over here. Most of the time, most of the acids are easy. When I ask my students to come up with the names or the formulae or the reactions with ethanoic acid, it becomes a little difficult for them because ethanoic acid is an organic acid and it's treated differently. Let's say we started off with magnesium oxide. We have magnesium oxide over here, and we are supposed to work with ethanoic acid, CH3COOH. How is the equation going to be? So it's going to be MgO plus CH3COOH. Remember, we're going to take 2 of them because the magnesium has a positive 2 valency. So it would be CH3COO twice Mg plus H2O. That's how we come up with the equation. This is a common equation in past papers. And as this is not a part of the book and they have taken easier acids such as hydrochloric, nitric, or sulfuric, sometimes writing equations with methanoic or ethanoic acid becomes difficult for the student. Make sure you note an example equation like this one on the book and do give it a try when you're preparing for exams. As far as the equation is concerned, I think it's simple enough. We understand this one is a solid, This one is aqueous. This one is also aqueous. And finally, this one's a liquid. But coming up with the names, it's easy. This is magnesium oxide. This is ethanoic acid. But this one is magnesium ethanoate. As we studied on the previous page, the ethanoic acid salts are known as ethanoates. So this is magnesium ethanoate, also giving water as a product. If the salt comes from acid and alkali and produces salt and water, remember both products are neutral. That's why most of the time this reaction is known as neutralization reaction. I hope that clarifies it. So let's move on to the next topic then. The next topic is something which is a part of chapter 5, and almost everything written over here is also a part of chapter 12. So you can either skip the entire 5.7 and you can prepare it in chapter 12, or you may do it over here and go for revision in chapter 12. Well, I'm not going to leave it. I'm going to go through the important parts of it. Starting off with 5.7, acids and alkalis in chemical analysis, it's pretty important that we go for the basic information, such as test for carbonates using acids. As carbonates react with acids giving off carbon dioxide, which fizzes or gives bubbles, it's easy to go with this kind of reaction. When it produces carbon dioxide, we can pass the gas into lime water, and the lime water turns milky or cloudy. You can use the word milky, you can use the word cloudy, both words are acceptable. If the lime water does turn cloudy, the gas is carbon dioxide and the substance is a carbonate. So that's a pretty good test to check for a carbonate substance. Add acid to it. If it fizzes, there is gas being given off. Collect the gas, pass the gas through lime water. If the lime water turns cloudy or milky, the gas is carbon dioxide, the substance is a carbonate. So these kinds of tests are known as analysis tests. These kinds of tests gives you visual observations for which you can come up with the answers what the salts are. Analysis are the tests in which we usually don't know what we are dealing with, and with the help of simple chemical tests, we can come up with the answer what kind of salt or what kind of substance are we dealing with. Like testing for a carbonate, you can easily tell after the test that the gas produced was carbon dioxide and the substance used was a carbonate. But that only clarifies a negative part or the anion of the substance. Because carbonate is the negative part of the substance, there must be a positive ion over here, and the chances are it would be a metal cation. So for testing for metal ions in salts, we use alkalis. And that's one of the most important chemical analysis part. This is the reaction for passing the gas through lime water and the lime water turning cloudy. So testing for the positive ion, there can be colored precipitates. We use hydroxides, and in alkali we use sodium hydroxide. We may also use ammonia solution for the same purpose. So these substances, copper 2 salts give a light blue precipitate, iron 2 salts give a light green precipitate, iron 3 salts give a red brown precipitate, and chromium 3 salts give a gray green precipitate. You're supposed to memorize all 4 of these colors for these 4 specific ions. So it's pretty easy. The color of the precipitates tells you what kind of ion we dealt with. So if it was iron 2, upon reaction with sodium hydroxide, it would produce a precipitate. Precipitate means something that is insoluble in water. So you would see the symbol S written next to it. So it's the southern formation of the solid that forms in a reaction and tends to settle down as it's heavier than water and insoluble as well. However, there may be white hydroxide precipitates. Some substances that make white hydroxide precipitates are calcium, zinc, alumina. Take a look. Zinc, sodium reacts to form zinc hydroxide. This is a solid. This is actually a white precipitate. If the precipitates are white, we might not be able to distinguish between these three, but we do have our way in differentiating between them. When an excess of sodium hydroxide is added, the zinc and aluminum hydroxide precipitates redissolve to give colorless solutions. The calcium hydroxide precipitate does not redissolve. That's how we bifurcate calcium out of this list. But we're still not able to bifurcate between zinc and aluminum. What are we going to do then? We have another test actually to work with it. To identify zinc or aluminum, the test is repeated with ammonia solution. The same white precipitates are produced. However, with excessive ammonia solution, only zinc hydroxide precipitate redissolves. Aluminum doesn't. So we first use sodium hydroxide. Everything redissolves except calcium. We then use ammonia solution, and aluminum tend not to dissolve while zinc redissolves to give us a very good idea and bifurcate all three of them. Although all three of them were white, but that's the way we bifurcate them. Ammonium salts, however, are slightly different. They are different from metalines, so we handle them differently. We react them with alkyl solutions and they produce ammonia. Ammonia gas can be detected with a damp red litmus paper, and as ammonia is an alkaline gas, it turns the damp red litmus paper blue. So it's a pretty easy test. So we use an alkali, it produces ammonia gas, there would be some bubbling, but we need to quickly check it with a damp red litmus paper, which turns to blue. This gives us the idea that the gas is ammonia and the ions were ammonium ions. That way, we can check all positive ions, be it an ammonium ion or an other metal ion. This completes 5.7 for us too. Any questions so far?